Hello students, now in this video we are going to see what are finite sets. Okay, one definition which we already know about a finite set is that if you know exactly how many elements are there in a set, that means it's a finite set. That is what if any set contains finite number of elements, then a finite, if not then infinite sets. Okay, but another thing is slightly in terms of a bijection and one onto maps. Here is another definition, and it says that if there any set A is said to be finite if either A is an empty set or there is a bijection F from A to In. And what does this In looks like? I had explained this in the class also. In, it looks like all the elements from 1 till n. Okay, all the natural numbers 1 2 3 till n. Like for example, I4 will contain 1 2 3 4 4 number of 4 elements total. I3 will contain 1 2 3 natural numbers 1 2 3. Okay, so similarly I5 will contain 1 2 3 4 5, that is total 5 elements. So that means what? A is said to be finite if there exists a bijection between A and this in set. It is a finite number of set. Okay, and in the starting of this chapter, in the class also we had seen already that we say that any two sets A and B have the same cardinality if there exists a bijection between A and B. Okay, and we had seen various kinds of intervals and all, real numbers and intervals where there was same we had constructed bijections between the two intervals. Okay, so similarly what happens is the same concept goes here. If there exists a bijection from A to In, that means the cardinality of A is same as the cardinality of In, and I know that cardinality of In is n since it contains n number of elements. So this is how the concept goes. Okay, and also we had seen another thing, I had explained in the class also. If m is less than n, then there is no 1-1 map from In to Im. Okay, I'll just explain this in slightly other words. If I want a 1-1 map from one set to another set, let's say some x to y. Okay, if that f has to be 1-1, that means from here there should have, for one element over here there should have another element. Okay, for one element over here there should be another element. For one element there should be another different element. That means for f to be 1 1 there should be, if जर हांगासर चार elements आसा जाल्यार हांगा सुद्धा चार तरी आसचीच पडटली different, because each and every element will go to a separate element. Okay, like here there can be 10 elements, but here there can be at least 10 elements. Okay, uh, 12 असल्यार चलता, but ती 10 तरी separate आसपाकूच जाय. Okay, otherwise what will happen if there are only two elements over here and there are, let's say, three elements over here? What will happen? One will go here, one will go here, and the third one will go to either this or this. That means what it will get? The answer will get repeated. So that means what? The function will not be 1 1. So what it says is if this one has a lesser number of elements and this one has, let's say, higher number of elements, then there cannot be a 1-1 map between both of them. That is from In to In. That is if this has higher number of elements and this has lower number of elements, then there does not exist a 1-1 map. That is what it says. Okay, and the reason is this, that the the elements will have repeated answers like this. Okay, and this is what we don't want, and that is what we are going to prove, that there does not exist a 1-1 map. And to prove this we will proceed by induction on this m. Okay, n will be some fixed number and I m, this m we will use the induction. Now for induction I know what we do. We consider something true for m is equals to 1. We assume something for m, and then we prove something for m plus 1. This is what we are going to do now. Okay, and for that I will create a statement. Let p of m be the statement. Given n greater than m, no map from no map f from in to im is 1 1, where n is again greater than this m. Okay, so from higher number of elements to a lower number of elements, there does not exist a 1 1 map. This is what we want to prove. So for that, what I will do is I will consider some n greater than 1. Okay, that is some random n, and I will take m is equals to 1, because that becomes the first step of our induction. So now what I will do is I'll construct a map f from in to im. Now if m is 1, that means it will look like I1. Okay, im will look like I1, and that is this singleton set 1. Okay, so it will look like this. Okay, so what will happen from in contains 1, 2, 3 till n number of elements, and there exists this set 1. So that means f of 1 will be 1, f of 2 will be 1, f of this n will also go here, and it will be 1. So that means what I will get is f of 1 is equals to f of n, which is equal to 1, but 1 not equal to n, because I have taken n strictly greater than 1. Okay, so that means what? This is not 1 1 map. Okay, and that is what my p of 1 states. P of 1 in the sense p of 1, if I substitute here, it says n greater than 1, no map from in to im I1 is 1 1. So here also no map is 1 1. So that case, base case, that p of 1 is true. Okay, now what I will do is I will assume that p of m is true. This is what I will assume. That is, I will assume that from in to im there is no 1 1 map for n greater than m, and I will try to prove for m plus 1. Okay, now what will be the p m plus 1 statement? That there exists a 1 1 map from in to im. So for n greater than m plus 1, what I will do is I will construct a f from in to im plus 1 map. Okay, and I will say that let that f be 1 1, and I will create a contradiction. Okay, now there are certain possibilities for f. Here this I1 contains 1, 2 till n. Okay, so now I will just think for this f of n. What can be the possible values of this f of n? So I'll just take case 1. Okay, see now how does that in looks like? In will look like a set. Okay, 1, 2, 3, n minus 1 and n. Okay, out of that, this n minus 1, this is a smaller set I n minus 1, and this is a bigger set I n. Okay, now what I will do is I have this I m plus 1 set also. I m plus 1 set. I m plus 1 set will have 1, 2, 3, m and m plus 1 at the end. Okay, and this is the smaller set, which is a subset of it, is going to look like im. So now one of the possibility is this n is mapped to this m plus 1. That can be the one of the possibility. Okay, so one case is f of n is equals to f of, so f of n is equals to m plus 1, and all the elements inside, they have been somehow mapped to this im. That is in minus 1 has been mapped to im, and that is 1 1, and this n has been mapped to m plus 1. Okay, and what I will consider this, whatever which is mapped inside these smaller subsets which are mapped to each other, I will say that it's a function g. Okay, I will say that it is a function from in minus 1 to im. Okay, where it is given by g of some j is equals to f of j. That basically it is the same function, but since same function f, but what has been happened is I have just changed the intervals. Okay, I have just taken the subsets. In minus 1 is a subset of this im plus 1 is a subset of im. Oh, sorry, im is a subset of im plus 1. So basically what happens is, since the domains and the codomains are changing, although this f and g are basically same, but still what I'm doing is I'm just redefining them. Because for f and g to be equal, what should happen? The domain should be equal and their codomain should also be equal, but they are not happening the same in this case. Okay, so that's why I am just mentioning them as two different functions, f and g. Otherwise the definition is one and the same. Okay, so now what I'm going to do is, from here, see g, I what I have assumed already for p of m, that such a thing cannot happen from any if c n is greater than m plus 1, that means n minus 1 is greater than m for sure. Okay, and it's a wrong statement that n minus 1 to im there exists a 1 1 map, because we have assumed that for such a thing, I have assumed that there does not exist such a map from in to im. Okay, p of m is true. There is no 1 1 map from this stuff. Okay, so now what I can say is it's a contradiction. Now since G is 1 1, it is a contradiction to P of M. Now, what is the second case? Here in the first case, what I had assumed that f of n I'm getting as some m plus 1. Okay, now here in the case what I will assume that f of n is equals to some r which is less than m plus 1, so it can take some values from 1 2 till m, but not m plus 1. M plus 1 value has been covered in this session. Okay, so that means what? But okay, so what happens for out of this set, f of n is some value from here. Okay, so but this m plus 1 should have some answer in the original domain. Okay, so it should have some pre-image such that f of something should be equal to this m plus 1. Okay, so what I will do is I will say that there exists some k which is less than n, obviously less than n cause the highest number is already mapped to some r. Okay, so what I will do is there exists some k less than n such that f of k is equals to m plus 1. Okay, so now again here what happens is that this becomes a contradiction. Why? Because this for this what I had assumed for such a n where less than where any k is less than n, there does not exist a function which is 1 1. Okay, so again this is a contradiction. So that means what? Again, I cannot say that it's a 1 1. So therefore what happens is that this p of m plus 1 which says that there exists a 1 1 map is false. Therefore there does not exist a 1 1 map from in to im if n is greater than m. Now this question can also be molded in such a way in some question papers. I had just seen one doubt. If this, that is the cardinality of A is greater than cardinality of B, then show that there does not exist a 1 1 map from A to B. It is one and the same for n greater than m, in to im. The same definition has to be done, but only thing is that for in it has to be replaced by A, this im has to be replaced by B. Okay, now there exists another proof, a similar proof. This one is for 1 1. Now we'll see what happens for onto. If m is less than n, then there is no onto map from I m to in. That is what I will say. If this one is a smaller set, this one is a bigger set. For being onto, what should happen? For every element over here, there should exist some element over here. Yes or no? Okay. But see, if here are the elements which are lesser, and here there are more number of elements, it will happen that for some of the elements over here, there won't be any element here. Okay. So that means what? Obviously, it is not going to be onto. So what I will do is, I will just prove this. Now let m less than n, which is already given, and f from im to in be onto. I will assume that it is onto. I will define a g from in to im as another function. From here to here, I will define some g. Okay, such that for some r belonging to in contains all the elements from 1 to n. Okay, I will assume that g of r is equals to minimum of f minimum of f inverse of r. Okay, so what I will do is, I will just claim that g is 1 1. Now to show something is 1 1, what I will do is, I will take two elements which are here. Let's see, some r and s. I will assume that g of r is equals to g of s, and somehow I will try to show that r is equals to s. Okay, so what I will do is, for r comma s belonging to in, what I will do, I'll assume g of r is equals to g of s. And what is g of r? It is minimum of f inverse of r, and g of s is minimum of f inverse of s. And since they are equal, I will give some value k. And this k is going to belong to im. Okay? Because g of something is belonging to im. Now, that means what? F inverse of R is a set, F inverse of S is a set. That means K belongs to F inverse of R also, and it belongs to F inverse of S also. That means it belongs to the intersection of both of this. Okay, so that means what? K is equals to F inverse of R also. That is what? Sorry, K belongs to F inverse of R. That means F of K is equals to R. This is what I know from functions chapter. Pre-images of subsets, inverse images of subsets under function. Okay, and from here this part I know f of k is equals to s. Okay, so that means what? Therefore r is equals to s, I know, otherwise it wouldn't have been a function. Therefore what I say is g is 1 1. Now if g is 1 1, g was from in to im. Okay, in to I had explained, I had constructed it, and this n was greater than m. And just in the previous lemma, what I had seen, if this number is greater than this number, then there cannot exist a 1 1 function. So if it cannot exist a 1 1 function, and now if I'm getting that g is 1 1, that means it's a contradiction. Okay, now if it's a contradiction, therefore such a map cannot exist. If such a g cannot exist, that means such a f also cannot exist. Okay, that means what? This f is not onto. Basically such a onto function cannot exist. That is what? There is no onto map from im to in if m is less than n. Okay, so now what we have seen, if f is from im to in, for f to be 1 1, we had discussed this in the class also. For f to be 1 1, what should I have is, this n should be greater than or equal to m. This is what I know. For onto, it should be n should be less than or equal to m. Okay, sorry, yes, n should be less than or equal to m. Okay, so that means what? For bijection, I should satisfy both the cases. That means for bijection, it should be n should be equal to m. So I can have another lemma: if f is a bijection from in to im, then m is equals to n. So if this proof is being asked, then first two, both the proofs should be done. Okay. So this was all about the finite sets. See, these same questions can be twisted again. Okay. This question same can be repeated like that, if cardinality of A is less than cardinality of B, then there cannot exist a map, a one onto map from A to B. Such a question can also be asked. Or if there exists a onto map from A to B, then cardinality of A should be greater than cardinality of B. Prove. This is what also can be asked. So what you have to assume, that let this be less than b and show that that does not exist onto maps. So basically there can be total 5 to 6 kind of questions or can be asked on these three lemmas. Okay,